So that's a lot of noise. And you know, conducted noise is a real thing. You have these fantastic switching power supplies that are in everything today. Everything from your dishwasher to your refrigerator, your range, you know, air conditioners, and of course the ATX computer power supplies are loaded with high power switching components that generate all kinds of radiated and conducted noise. Now, the first order of business is you want to eliminate noise from getting out into the world through the power line. So this particular supply here, you can see that right on the IEC input, they have a fairly elaborate filter. It's a two-stage common mode filter, and it looks like it's got both X2 and Y2 capacitors, as well as a pair of common mode transformers. So this is called a two-stage common mode RFI EMI filter, and it's right on the input that you bring in your power into the supply. Now, a smaller, cheaper supply might not have as good a filtering setup. This one, they've jumpered across where a single-stage common mode choke would normally go. And they've also eliminated a couple of the capacitors. So this particular power supply, being a smaller one, they cheaped out and didn't do any power line filtering whatsoever. So let the buyer beware. They're going to save some pennies whenever they can with this stuff. So let's talk a little bit about conducted noise and how these line filters really work. And we're going to build one and attempt to tame my monster dishwasher that's putting out all kinds of really cool noises onto the line and pretty much upsetting any radio that's plugged into the power line. Okay, so there's little doubt that my new dishwasher is fairly evil. I need to make some kind of filter to stop that noise right at the dishwasher so that it doesn't get on the line and be picked up by everything. It's a real noisemaker. So there's a brand new line going over there that's been run by the electrician. There's a brand new outlet it's plugged into. That is where the noise is being injected into, and it's going straight back to the main box for the house. We can probably sniff that out and figure out what that noise is. But you could hear it's coming right in the line. It's not radiated. Well, it probably is radiated, but it's the conducted that's the major source of the noise, not radiated noise. So we need to try to stop that conducted noise. Now, I wanted to build a little box that would go under the cabinet so that it would plug right into this box, and then that box would plug into the new outlet that's been installed. So I've gotten kind of an oversized box here, you know, from the hardware store. And I've got an outlet. This outlet is going to be, it's probably the wrong size. This is a 20 amp outlet. I probably should have gone with a 15 amp, but that's fine. It's probably very tempting just to take this two-stage line filter out of this 500 watt power supply and put that in a box and call it good enough for the dishwasher. And that might actually work. I don't know how much this dishwasher draws, but typically dishwashers today draw somewhere around 7 to 12 amps. Okay, could be you know, 10 amps, something like that. Just depends on the cycle they're on. But they're all made to run on a 15 amp circuit. So typically you want to have heavy enough wire in these transformers to be able to pass, you know, 10, 12 amps with no trouble. Now, this wire looks a little bit light to me, even though it looks like it's number 20, and number 20 wire is probably capable of 7 or 8 amps in chassis wiring. I think it's too light for the dishwasher, so I'm not going to steal it out of there. Instead, I'm going to make my own transformer, and I have a big type 77 ferrite core here. This big boy should be pretty good for a transformer, and I'm going to use some number 14 or number 12 enameled wire see how many turns I can get on there with a common mode choke, and hopefully I can achieve 1 millihenry of inductance on each of the windings. So the filter is going to have some features. These are the X caps. I'll probably have 3 X caps. The common mode choke takes care of common mode noise. 2 differential chokes that they take care of the differential type noise. I've got the 2 Y capacitors and a 470K resistor right across the line. So I'll use my Dremel tool to carve up this board a little bit, and hopefully it'll fit in this box. So using the Dremel tool, I've carved in a little pattern here that can hold the components. I've kept the ground as a spine down through the middle. We're looking at the beast. So this guy is made with number 14 enameled wire. It's wrapped with Kapton tape. The 2 toroids in the differential chokes have plastic encapsulation around the toroid already, so no need to wrap those. This is a compound filter, common mode choke, differential, takes care of both types of EMI. There's X capacitors on the input, the middle section, and the final section. There's a snubbing resistor across the line on the input. There's 2 3300 puff Y2 capacitors in the center section, and 2 4700 puff Y2 capacitors on the output. This should give some attenuation in the shortwave band where we're really looking. I was able to find something online. It's a dual section. This is a dual common mode filter that I found online. Now supposedly this little filter does 25 amps. This is flat wound wire. It's not enameled, so it's a little bit deceiving. It probably handles more current than you would think. However, compared to the Beast, I trust the Beast a little more. So I will try this, and we'll see how this does against the evil Dishwasher.
Okay, let's look at a typical AC line EMI filter. L1, L2, C1, and C2 attenuate the differential mode noise. T1, C3, and C4 reduce the common mode noise. Absorbs energy from transients and surges. R1 basically limits the inrush current. R2 discharges C1 and C2 on power down. And the fuse, FS1, protects against downstream shorts. So not all filters have all of these components, but most of them will at least have the common mode choke and C2 and C3 and C4. So here's a 2-stage common mode filter. So it's got 2 identical common mode stages, and it handles the differential current simply with the capacitors that are here. This has both common mode and differential features, but the differential features are taken care of by the capacitors here, here, and here, and the common mode features are the 2 transformers and these 2 capacitors. I was able to figure out how something as small as this could handle 25 amps as they advertised on Amazon. This is not round copper wire, it's flat wire. That's how they're able to boast 25 amps. Well, I don't really believe that, but I did buy a couple of these to try them. In the end, I did decide to build my own common mode filter, and I went common mode filter on one stage, differential mode on the second stage. Now my differential mode components are this capacitor, this capacitor, this capacitor, and these 2 chokes. My common mode protection is this transformer and these two common mode caps. So basically the common mode and the differential mode stages must be symmetrical. So identical differential mode chokes on each of the line and neutral lines. Try to maintain balanced impedances, because any imbalance basically causes some of the common mode noise to be transferred into differential noise. Here's a typical common mode choke. It's a common mode choke. It's not a transformer. We're putting the current through each of the windings and looking for common mode rejection. So how do these filters play with a GFI or GFCI outlet? Basically, with regulations that we have now, between regulations and insurance companies, driving all the time, more safety, more safety. The GFI, or ground fault interrupt, or as we say now, GFCI, ground fault circuit interrupt, outlets are mandated for most areas in your house. Even for your appliances like that nasty dishwasher I have, or the refrigerator. And a single line is required for each appliance. So for instance, the fridge and dishwasher are supposed to be on a separate circuit breaker. And they should each have their own line, and each should be supplied with a GFCI outlet. So the international safety agencies, basically they have a whole class of different maximums, and they're measuring or limiting the total RMS current introduced into the earth from either line or neutral to a total typically of 0.25 milliamps, half a milliamp, perhaps as high as 3.5 milliamps, depending on the type of equipment and the installation category. For instance, what is it, an enclosed device? Its earthing and its internal isolation scheme. Now, here's the maximum permitted for a Class A GFCI. Notice how most the outlets are well below this limit. That means they're a little bit touchy. So you're going to find that you're going to be able to trip these things quite easily. So even though you can allow up to 3.5 milliamps, it doesn't mean that your outlet isn't going to trip. So basically, EMI filters alone will not generally trip an outlet unless the capacitors are presenting more current, usually on transients, than the outlet will allow with its detection system. So if we solve for X sub C on these capacitors, we get about 79 microamps per nanofarad. This gives us a maximum allowed capacitance of around 6.4 nanofarads for half a milliamp, or 44 nanofarads for 3.5 milliamps. So a 0.0047 Y2 cap is likely to pop the GFCI if you have surges like from a pump or something like that. Probably won't do it on a radio, however, since it's a static type situation. The Amazon filter unit I got from China uses a pair of 0.0033 microfarad or 33 nanofarad caps for the Y2s. So if I had to guess on older ham gear that used to have the 0.047 microfarad caps or a 0.1 cap from neutral to chassis, you probably should replace them with Y2 safety caps no larger than an 0047 for US power. But don't get too whipped up. A 3300 puff has a self-resonant frequency around 29 megahertz, which is just about perfect for the shortwave range. So this capacitor is going to have an X sub C that keeps going down, down, down until it really goes down at 29 megahertz. So in our filter, a pair of 3300s is a good choice. 4700s are also a good choice. But in my original filter, I actually had 4700 and 3300, and that got upwards of the 0.01, and that was enough with surges like the pump starting in the dishwasher to pop the GFCI.
So here's a ordinary 15 amp outlet, and here's a 20 amp outlet. They look the same. Basically, just one is approved for a higher current. It might have slightly better hardware inside one than the other. Either one would work okay for this. Now in this outlet cover that's bumped up, notice it has these two tabs. Those two tabs you break off. Those are nuts, actually. Those are used to go in back of the outlet to secure it to the front of the plate. So we'll break those off and use those as the nuts. So the nuts just snapped right off. Using needle nose pliers, they just came right off. So I've moved one of the nuts to where it's going to be, and you put the screw in the front. There we are. Pretty straightforward. Okay, so that makes a pretty solid looking setup. Next we have to have a 3-wire cord that's at least number 14 wire, and it's just going to be a little pigtail coming out of this long enough to go into the nearby outlet with the appropriate Hakko grommet for the cord. So we need to drill that into the chassis. So I'm just doing some simple measurements, and I figure the bottom of the broadcast band is probably a good place to take my measurement. This filter really cuts in nice, and by the time you get to the bottom of the broadcast band around 540 kilohertz, it's exhibiting 60 dB of rejection at that frequency. So it's going to give you 60 dB minimum at the bottom of the broadcast band in rejection. Okay, here we are. We've got both the from scratch filter over here and the store-bought filter that I put in this this box. Looks like I've got the outlet front cover wrong. This is made for a GFI outlet or a modular outlet, but that's okay. It's fine for testing. And we're going to try both of these on the dishwasher. Let's see which one works. So the combination of the 0033 and the 0047 capacitors, the Y2s, that go from hot and neutral to ground combined were enough to put enough return current to actually set off the GFI outlet and trip it. So the smaller unit, the 25 amp job that I got online, only has the two 3300 puff caps in the middle. So I'm going to remove these two 4700s, and we'll test it again. So this is a power source project. We're dealing with the AC line. We've got a power outlet. This is not a bad thing to have peer reviewed. And I have a good friend, Spencer Webb, who is not only a crackerjack EE, but also RF and antenna guy. Boy electrician, you name it. He's a good guy to pass circuits and ideas around with. So he was looking at, first of all, the Chinese job here, this 2-section filter I got from Amazon, and you can see it's got 3 terminals on each end. One is line, one is neutral, and one is ground, and line, neutral, and ground, the load side going to the output, which is the outlet. Similarly, I copied their example. I have a cord going into the input of the filter, and on the load side I go to the outlet. So he said that I was breaking some rules, and that we need to never break ground. Even though ground is going through the board, you're still breaking ground. So in order to ensure that even if the board vaporizes, that you still have ground, the only way to do that is to put a big old lug on the case. So I'm going to add lugs to this the green wire from the cord, the green wire from the outlet, the green wire from the board, each end, are going to go to that lug. And that will ensure that we have a good ground and that it's wired in a little bit safer manner. Thanks, Spencer. Okay, this is the S120 at the bottom of the broadcast band. No external antenna, just using the loop antenna. And it's picking up line noise. Now all I'm going to do is plug it into the line filter. Now the line filter, this is the worst place for it, at the very end of the line. Plus this is only a 2-wire cord, so it really is not effective. So this is the wrong way to use the filter that I built, but let's see what it does. Okay, even though we're doing everything wrong here, this is only a 2-wire cord, the filter, even right next to the receiver, is cleaning up a lot of that mess. Let's try it again. Let's go back to just the strip again. Okay. You can imagine how much more effective this would be the further up the line you put it.
People really did need for the news, breaking news.
Okay, I've got this on band 4. Volume's up like it was before, but this time we have the filter upstairs. So let's start that dishwasher. Hope you've enjoyed this little video on EMI conducted type filtering and how it might help you against some of those noisy appliances you have in your house.